So in the previous video, I gave you a little bit of background on oxidation-reduction reactions as well as oxidation states, and we saw how we can use rules that would assign oxidation states to help us figure out the elements that are being oxidized and reduced for somewhat complicated chemical reactions. So chemists think that oxidation is a loss of electrons. Just write that here. For chemists, oxidation is loss of electrons. But biologists actually think it's a gain in hydrogen. So for those of you, hopefully this video lecture is going to be geared towards those of you who have some background in cellular respiration, cell biology, and if you do, which hopefully if you're watching this you do, you probably noticed that in glycolysis and the Krebs cycle you have several instances in which NAD plus is reduced to NADH. And you might be thinking, okay, how is this this is a gain in hydrogen? How is this a gain in electrons? I should have said here, reduction is gain of electrons. So if a gain of hydrogen is a gain in electron, if this is reduction, so this is an example of reduction according to biologists. Reduction from biologist's point of view. Not POW. We're not talking about prisoners of war here. Okay, so this is an example of reduction from a biologist's point of view. So we're gaining hydrogen. How are we gaining electrons here? Aren't hydrogens usually protons? Well, that's a hydrogen anion. That's the H plus ion. This is a proton, so a hydrogen stripped of its one electron. But alternatively, there's a hydride ion, the H minus ion, which is a hydrogen which instead of having one electron has two electrons. And that's really the hydrogen that's involved here in the conversion of NAD to NADH. And if you have some background in organic chemistry, I will here show you the mechanism whereby this actually occurs. And you'll see it really does involve electron transfer. So here's the structure of NAD here. And you'll notice it's NAD, this is NAD plus, and the positive charge comes from this formal charge being on the nitrogen atom here. Okay. And this is nicotinamide. This is the namesake of the N in NAD. Nicotinamide stands for nicotinamide adenine dinucleotide, but this portion here is the nicotinamide. I'm just redrawing it here. So I'm just going to redraw NAD with just showing this other stuff as an R group. So with the emphasis on nicotinamide, because this is really where the action is in the conversion of NAD plus to NADH. And when you have the R group, this lone pair of electrons is, or actually this this lone pair of electrons is not present when you have the R group there. And that's why this has a positive charge, because nitrogen has a valence number of 5, and here you can see it makes 3 bonds and has a lone pair 5 minus, so it's involved in I guess it has It has half an electron from each of these three bonds, and then two of its own. So, or I should say half a pair. So one electron from each of these three bonds, and two of its own. So it has 5 electrons here, but in this case it only has 4. It's bonding to 4 groups but missing a lone pair, so it's going to have a +1 charge. If you know how to calculate formal charges, this should make sense to you. If not, don't worry about it. But anyway, this is I'll draw the amide group here, or the amide group. This is another representation for NAD+, showing you really where the action happens. And at each of these carbons here, there's a hydrogen as well. So in the conversion of NAD to NAD+, you'll have a 2-electron hydride transfer. So you have this H- anion, and it is going to attack at this carbon. This H- anion is negatively charged. It's a nucleophile. It's going to attack at this carbon here. And then when that happens, you'll get moving of these pi electrons here. With these pi electrons to empty orbital on nitrogen. And what you'll get as a result, is, oops, this should have a nitrogen here. Nitrogen will get its lone pair back, will no longer have a formal charge. You'll have an additional hydrogen on this carbon. These two will still have one hydrogen. This amide group will remain unchanged, and I guess I could write the lone pair electrons here. So you do gain a hydrogen here at this carbon. So this is NADH. This is NADH, and this was an alternative representation for NAD+. All we did was, all this stuff here doesn't participate in the conversion of NAD+ to NADH. So I just represented it as a generic R group. So this 2-electron hydride transfer is what results in the conversion of NAD+ to NADH. And yes, it's a transfer of hydrogens, but also you're gaining electrons at this carbon here, and there's an overall gain in electrons. And you can see that by noting that this has a formal charge of 1. This nitrogen has a formal charge of 1, and that goes away, and there's really no other charge here. So another way I could write this plus 2 electrons, and at plus 2H+ as well. I could, or sorry, plus 2 electrons plus 1H+, because a hydrogen is equivalent to a proton and 2 electrons, and a proton is the same thing as H+. But or I could just represent this as, NAD+ plus a hydride anion gives you this. So yes, reduction in biology is the addition of hydrogens, but this is equivalent to a gain in electrons, which is consistent with the chemistry definition of reduction here. Where'd I write it? Reduction is a gain of electron from the chemist's point of view. Now, what about if we wanted to think of oxidation from a biologist's point of view? Well, if we reverse this reaction here, so let's say this were to lose, let's say this this carbon-hydrogen bond were to break and this hydrogen were to take its electrons with it, right? Then what would happen? Well, these pi electrons here would move here. These on the nitrogen would move here. And once again, you'll get what we started out with here, this NAD+. This hydrogen will leave and take its electrons with it. And of course, this amide group will remain unchanged. And the nitrogen will once again bear a formal charge of +1. So when you lose hydrogens, I can write up over top of here minus H minus the hydride ion. When you lose hydrogens, remember the hydrogen's going to take its electrons with it, so you're really losing electrons as well. And yes, that's oxidation from a biologist's point of view, but it's also oxidation from a chemist's point of view, because not only are you losing hydrogens, you're also losing electrons, because the hydrogen is taking its electrons with it. And when you have reduction, the hydrogen is bringing its electrons along with it. The hydrogen is, and it's really not just a hydrogen, it's a hydride anion. So it has a pair of electrons. It's bringing both electrons to form a bond with the carbon. So you're gaining a pair of electrons. And conversely, in oxidation, you're losing a pair of electrons. So hopefully that clears up any confusion between the chemists and biologists' views on oxidation and reduction. Hopefully shows you that they're essentially the same thing.